So today we're going to do some review for the midterm, which is a week from today. I sent out a list of problems, though I see that there's one typo I should correct. Just the first group are not proofs, they're problems. So any questions before we start? No? Okay. So let me just start to go through the numerical exercises. Problem 1 is to factor 1218. So this is just a little bit of arithmetic, which you can do it by hand. So the first thing you might observe is 1218 is even. So it's 2 times 609. I think I'm doing this right. And 609, just looking at it, looks like it's divisible by 3. So that's 2 times 3 times 203. Let's see, what can we say about 203? It's not even. It's not divisible by 3 or 5. Is it divisible by 7? I don't know. 7 into 203. Yeah. So this is 2 times 3 times 7 times 29. And that's the factorization. We factored this into a product of prime numbers. Okay. Any questions about this? Problem 2 is to compute the greatest common divisor the GCD of 1218 and 616 using the Euclidean algorithm. So you take 1218, and the first thing you do is divide it by 616. So this is 616 times 1 plus a remainder, I think, of 602. 602 plus 616 plus 602 is 1218. And then I take 616 and I divide it by 602. That goes once and leaves a remainder of 14. And then I take 602 and I divide it by 14. Let's see, what do I get? I don't know. Let's divide 14 into 602. 4 times 14 is 56. 42. 14 into 42 goes 3 times. So this is 14 times 43 and a remainder of 0. So the last positive remainder is 14. So the GCD of 1218 and 616 is equal to 14. That's the answer. Any questions about this? Part Problem 3 is to write this greatest common divisor, 14, as an integral linear combination of 12, 18, and 616 by reversing the Euclidean algorithm. So the GCD is 14, which is equal to 616 minus 602. And according to this, 602 is 1218 minus 616. So this is 2 times 616 plus minus 1 times 1218. So, or 1218 times minus 1 plus 616 times 2 equals 14. So this is of the form 1218x plus 616 y equals 14, where x is minus 1 and y is 2. Any questions? Okay. Problem 4 is to take a permutation, sigma, and write it as a product of disjoint cycles and a product of transpositions. So this is the permutation in S9. So this is a function from the set of the first 9 integers to itself. That's 1 to 1 and on to 4, 5, 8, 3, 2, 9, 6, 1, 7. That's sigma. So if we look at sigma and follow the trajectory of 1, 1 gets sent to 4. 4 gets sent to 3. 3 gets sent to 8. 8 gets sent back to 1. So there's a 4 cycle in here. 1 to 4 to 3 to 8 back to 1. See, 2 is not here, so let's look at 2. 2 goes to 5, goes back to 2. So this is a 2 cycle or a transposition. See, the number 6 hasn't occurred yet. 6 goes to 9. 9 goes to 7. 7 goes back to 6. So here I have decomposed sigma into a product of pairwise disjoint cycles. I have a 4 cycle, a 2 cycle, and a 3 cycle. That's what makes up sigma. And now I want to write sigma as a product of transpositions. So this is part A. Part B, well, 2, 5 is a transposition. What about 6, 9, 7? 6, 9, 7, if I take 6, 9, and 9, 7, see, how does this act? This sends 6 to 6 to 9, 9 to 7 to 7, 7 to 9 to 6. So the 3 cycle, 6, 9, 7, is a product of these 2 transpositions. And 1, 4, 3, 8, let's see. Let's look at 1, 4, 4, 3, 3, 8. So this sends 1 to 1, 1 to 1, 1 to 4. 4 to 4, 4 to 3, 3 to 3. 3 goes to 8, goes to 8, goes to 8. 8 goes to 3, 3 goes to 4, 4 goes to 1. So 8 goes to 1. So this 3 cycle is a product of these 2 transpositions, and this 4 cycle is a product of these 3 transpositions. So sigma is a product of 1438, that's 144338, times the transposition 25. 697 is the product of 69 and 97. So that's the solution to part B. Here is sigma as a product of disjoint cycles. Here is sigma as a product of transpositions, which are not disjoint. And these don't commute. You have to do it in a specific order. And it can be done in more than one way, but you can't just rearrange these arbitrarily. Any questions about this? What about the inverse? Sigma inverse. So sigma sends 8 to 1, so the inverse has to send 1 back to 8. 1 goes to 8. 5 goes to 2 by sigma, so the inverse sends 2 back to 5. 4 goes to 3 under sigma, so the inverse sends 3 to 4. If 1 goes to 4, then 4 has to go back to 1 when you take the inverse. If 2 goes to 5, then 5 has to go to 2. If 7 goes to 6, then 6 has to go to 7. If 9 goes to 7, 7 has to go back to 9. If 3 goes to 8, 8 has to go back to 3. And if 6 goes to 9, then 9 goes back to 6. So this is sigma inverse. Questions about this? Okay. Problem 5 is to work out the full multiplication table. So for the set of permutations of 3 objects, doesn't matter what the objects are, they can just be 1, 2, 3. So the set of permutations is S3, which is the set of all permutations of 1, 2, 3. So what are the permutations of 1, 2, 3? First of all, there's the identity permutation, E, which sends everything to itself, 1 to 1, 2 to 2, 3 to 3. You can think of it if you like this. What's another permutation? Well, if you think of the 1, 2, 3 as being the vertices of a equilateral triangle, for example, you can rotate it by 2 pi over 3. So we might have the rotation sigma, which sends 1 to 2, 2 to 3, and 3 back to 1. Let's call this sigma 1. And you might have the rotation sigma 2, which rotates 4 pi over 3. So 1 goes to 3, 2 goes to 1, 3 goes to 2. So that's second, third permutation. You could also look at the permutation, let me call it tau 1, where you don't do anything to 1, but you flip 2 and 3. So 1 goes to 1, and 2 and 3 are interchanged. Or you could fix 2. 2 goes to 2, but 1 and 3 are interchanged. or you could fix 3 and 1 and 2 are interchanged. And there only are 6 permutations of 3 objects. So this is the whole list of all permutations in S3. And I want to calculate the multiplication table. So that's going to be a 6 by 6 matrix. I have E, sigma 1, sigma 2, tau 1, tau 2, tau 3, E, sigma 1, sigma 2, tau 1, tau 2, tau 3. And what I put in here is, in each given place, this times this. Now, the identity is the identity. Multiplying anything by the identity doesn't change it. So E times everything is E. E times E is E. E sigma 1 is sigma 1. E sigma 2 is sigma 2, and so forth. And sigma 1 times the identity is sigma 1, and similarly for all the rest. Okay. What is sigma 1 times sigma 1? So sigma 1 is you rotate by 1 step around, by 2 pi over 3 radians. So 1 goes to 2, and then you apply sigma 1 again, 2 goes to 3. So doing this rotation, if you think of this as a rotation of the points of an equilateral triangle, rotating and rotating again is a double rotation. That's sigma 1 squared. Sorry, that's sigma 1 squared. That's sigma 2. What's sigma 1 times sigma 2? When you do sigma 2, you rotate 2 steps around. And if you rotate a third time, you're back where you started. So sigma 1, sigma 2 is the identity. What's sigma 1 times tau 1? Maybe now we have to do some calculation. Sigma 1, tau 1. So sigma 1, if we write it out, this is the function 1, 2, 3, 2, 3, 1. And tau 1 is the function 1, 2, 3, 1, 3, 2. And this is composition of functions. Permutation is a function and multiplication is composition. This sends 1 to 1, and then 1 goes to 2. 2 goes to 3, and then 3 goes to 1. 3 goes to 2, and then 2 goes back to 3. So this is the permutation where 3 doesn't move, but 1 and 2 are interchanged. So that's tau 3. What's sigma 1 times tau 2? Sigma 1 tau 2 is 1, 2, 3, 2, 3, 1, preceded by tau 2. That fixes 2 and interchanges 1 and 3. So this permutation sends 1 to 3, and 3 goes back to 1. 2 goes to 2, and then 2 goes to 3. 3 goes to 1, and then 1 goes to 2. So this permutation fixes 1, interchanges 2 and 3, so this is tau 1. And what's sigma 1 tau 3? I have to calculate it. Sigma 1 tau 3. 1, 2, 3, 2, 3, 1. 1, 2, 3, 2, 1, 3. This sends 1 to 2 to 2. Oops, no, sorry. This is a 3 to 3. 3 to 3 to 1. 1 to 2. Oops. Let's see, let me do this again. And then 3. 3 goes to 3. 1 to 2, and 2 goes to 3. So 1 ends up at 3. 2 goes to 1, goes to 2, so 2 stays at 2. 3 goes to 3, goes to 1. So this permutation fixes 2 and interchanges 1 and 3, so that's tau 2. So that's tau 2. Okay. Let's do a few more. What's sigma 2 times sigma 1? I could work it out like this, but again, sigma 1 rotates once around the triangle, followed by a sigma 2, which is a double rotation. So when you move 3 steps, everything comes back where it starts. So sigma 2, sigma 1 is the identity. What about tau 1? Let's see, I want to finish this column. What is tau 1, sigma 1? So tau 1, sigma 1, tau 1, 1, 2, 3, 1, 3, 2, sigma 1, 1, 2, 3, 2, 3, 1, tau 1, sigma 1, 1 goes to 2, goes to 3, 2 goes to 3, goes back to 2, 3 goes to 1, goes to 1. So this fixes 2 and interchanges 1 and 3. So this is tau 2. Anyway, one can keep going this way. It's a useful calculation to do because it gives you a good feel for what these computations look like when we're studying products of permutations, right? And that gives you the multiplication table. Let me just do one more, maybe at random. Suppose, let's see. What goes here? This is tau 1 times tau 2. Tau 1, tau 2. Tau 2 fixes 2 and interchanges 1 and 3. Tau 1 fixes 1 and interchanges 2 and 3. So this sends 1 to 3 and 3 to 2. This sends 2 to 2 and 2 to 3. This sends 3 to 1 and 1 to 1. So 1 goes to 2, 2 goes to 3, 3 goes to 1. This is exactly sigma 1. So tau 1, tau 2 is sigma 1. Let's see what goes here. What goes here is tau 2, tau 1. Tau 1 fixes 1, interchanges 2 and 3. Tau 2 fixes 2, interchanges 3 and 1. So 1, 2, 3. 1 goes to 1, goes to 3. 3 goes to 2, goes to 2. Sorry, let me do this right. 1 goes to 1, goes to 3. 2 goes to 3, goes to 1. 3 goes to 2, goes to 2. So this is like the double rotation. 3, 1, 2 is sigma 2. And what we observe here is something we've observed before, but it's very important. Sigma 1 is tau 1, tau 2. Sigma 2 is tau 2, tau 1. And these are different. So multiplication of permutations is not commutative. The order matters. Multiplying tau 1 and tau 2 results in a different permutation from multiplying tau 2 and tau 1. Okay. Any questions about this? Okay. Upward and onward. Problem 6 is to use the division algorithm. If you take an integer a and an integer b, which is positive, and we divide a by b, we get a quotient q and a remainder r, where the remainder is non-negative and strictly less than what the number we're dividing by. So a number strictly less than b This is most b minus 1. So given a and b, do long division and find the quotient and the remainder. So if we take a equal to 591 and b equal 37, because when they're positive, you can just do division like you did in elementary school. 37 into 591, that goes once, 37. Bring down the 1, 2, 2. 37 into this, I think, let's see, maybe it goes 5 times. 5 sevens are 35, 5 threes are 15, and 3 is 18, and this is 6, 36. And that's the remainder, because you can't divide 37 into 36. So this says that 37 is equal to b, sorry, not 37, 591, that's my a, is equal to 37 times the quotient 15 plus the remainder 36. So this is my Q and this is my R, and 36 is non-negative and at most 36. Okay. What about minus 591? You might say just multiply by minus 1. You get minus 591 is 37 times minus 15 minus 36. But this cannot be the remainder because it's not, because it's negative. But I could say, let's see, 37 times minus 15 minus 36 is 1 minus 37. Right? 1 minus 37 is minus 36. So here I have 37 times minus 15 minus another 37. So that's 37 times minus 16 plus 1. And now, oops, sorry. Yeah, this was the quotient. This is the quotient, and the remainder is plus 1. Okay. Questions about that? Number 7 is to find the least non-negative residue of 83 mod 15. So we want to find a number R such that 87 is congruent to R mod 15, and R is between 0 and 14. But this is just another problem involving the division algorithm. If you divide 15 into 87, see, this goes 5 times and leaves a remainder of 12. 87 is equal to 15 times 5 plus 12. So 87 is congruent to 12 mod 15. Oops, I'm sorry. What I said is correct, but I just wrote down the problem wrong. The problem was 83 and not 87. So let me just correct that. So 83. If you divide 15 into 83, you get a quotient of 5 and a remainder of 8. So this is 12 times 5 plus 8. So 83 is congruent to 8 mod 15. Right? Now, if I take this and multiply it by minus 1, minus 83 is congruent to 15 times minus 5 minus 8. So it definitely is true that minus 83 is congruent to minus 8 mod 15, but minus 8 is negative. We want the least non-negative residue. But minus 8 plus 7 is 15. So minus 8 is congruent to 0 mod 15. So minus 83 is congruent to 7 mod 15. So 8 is the least non-negative residue of 83 mod 15, and 7 is the least non-negative residue of minus 83 mod 15. And if we want to check this, minus 83 minus 7 is minus 90, and that is divisible by 15. It's 15 times minus 6. So this checks. Questions about this? Problem 8. Solve the congruence, 7x congruent to 2 mod 11. So we want to find a number x that solves this congruence. Well, we could try different things. For example, we could make a table. So the congruence classes modulo 11, the choices for x mod 11 are 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. What is 7x mod 11? Or what is 7x? 7x multiplied by 7. 0, 7, 14, 21, 28, 35, 42, 49, 56, 63, and 70. What is 7x mod 11? What's the least non-negative residue? 0, 7, 14 is 3 mod 11. 21 is 10 mod 11. 28 is 6 mod 11, right? Because 28 minus 6 is 22, is divisible by 11. 35 is 2 mod 11. I can stop right now because what I just showed is that 7 times 5 is congruent to 2 mod 11, again, because 7 times 5 minus 2 is 35 minus 2 is 33, which is 11 times 3. So I can choose the answer. X equal to 5, or x is any number congruent to 5 mod 11. I could do this another way also. I could observe that 7 times 8 is 56, which is 55 plus 1, or 5 times 11 plus 1, is congruent to 1 mod 11. So 7 times 8 is congruent to 1 mod 11. So if I multiply 2, 7 times 8 times 2 is congruent to 2 mod 11. Or if you like, 7 times 16 is congruent to 2 mod 11. And 16 is congruent to 5 mod 11. So 7 times 5 is also congruent to 2 mod 11. So this was a slightly different way to solve the congruence. Right. Any questions so far? Let's look at problem number 9. We have two congruences. X is congruent to 3 mod 5, and X is congruent to 7 mod 11. We want to find a number that satisfies both congruences. And we know by the Chinese remainder theorem that this is possible. So how do we do it? Well, if X is congruent to 3 mod 5, X has to be a number of the form 5y plus 3 for some integer y. Right? That's what the congruence X congruent to 3 mod 5 means. It means X minus 3 is a multiple of 5. But we want this number also to be congruent to 7 mod 11, which is the same as 5y congruent to 4 mod 11. So we have to find a solution of that congruence. And again, one way to do it is you could just do it because 11 is a small number. You could just try all the possibilities for y. 0, 1, 2, 3, 4, and so on. And if you try them, you will see that y can be any number congruent to 3 mod 11. Because if you have y equal 3, 5 times 3 minus 4 is 15 minus 4 is 11. So y can be any number of the form 11z plus 3. And x is 5y plus 3. So x is 5 times y, 11z plus 3, which is 55z plus 11z, sorry. Y is 5y plus 3. So y is 11z plus 3. So that's 5y plus 3. It's 55z plus 15. 5 times 3 is 15 plus 3 plus 18. So x can be any number congruent to 18 modulo 55. Product of these two moduli, 5 and 11. It's just checked. That x equal 18. 18 minus 3 is 15, which is a multiple of 5. And 18 minus 7 is 11, which is obviously a multiple of 5. So any number x congruent to 18 mod 55 is a simultaneous solution of those two congruences. Okay. All right, let's keep going. Problem number 10. Factor some polynomials into irreducibles. So, you know, x squared minus 1 is x minus 1 times x plus 1. And x cubed minus 1 is x minus 1 times x squared plus x plus 1. And this is the factorization of x cubed minus 1. In fact, and x squared plus x plus 1, this is irreducible. This doesn't have any, this doesn't factor. At least It doesn't factor over the rational numbers. That's really all I want to say. In general, x to the n minus 1 always factors into x minus 1 times x to the n minus 1 plus x to the n minus 2, just the sequence of decreasing powers of x down to 1. So this you need to know, just general culture. This is this factorization of x to the n minus 1. And x cubed plus 1, maybe this is less obvious, but this also factors into x plus 1 times x squared minus x plus 1. And again, this is also irreducible over the rationals. X to the 8th minus 1, this is a little trickier, but 8 is 2 times 4. So this is the same as x to the 4 squared minus 1. And a square minus 1 factors, right? You always have a squared minus 1 is a minus 1 times a plus 1. So here, a is equal to x to the 4th. So this is x to the 4th minus 1, x to the 4th plus 1. And x to the 4th is the same as x squared squared. So this is like x squared squared minus 1 times x to the 4th plus 1. So this factors into x squared minus 1, x squared plus 1, x to the 4th plus 1. And you know this factors. This is x minus 1, x plus 1, x squared plus 1, x to the 4th plus 1. And that's as far as you can go. Okay. What about x to the 4th plus 2x squared plus 1? You can look at x to the 4th as x squared squared plus 2x squared plus 1. And you know that if you take a plus 1 and you square it, you get a squared plus 2a plus 1. So this is exactly of that form with a equal to x squared. So this is equal to x squared plus 1 squared. Or if you like, x squared plus 1 times x squared plus 1. And that's the factorization. Okay. Now, a polynomial looks similar to this is x4th, but just 1x squared plus 1. And it's not so obvious whether there's factors, but there is a certain trick you might see if you stare at this for a long time. X to the 4th plus x squared plus 1 is the same as x to the 4th plus x squared plus 1 plus x squared minus x squared, because all I did is add 0. But then x squared plus x squared is 2x squared. So that's x to the 4th plus 2x squared plus 1 minus x squared. And this we saw does factor. This is equal to x squared plus 1 squared minus x squared. And again, this is a difference of two squares. This is x squared plus 1 squared minus x squared. So this is the same as x squared plus 1 minus x times x squared plus 1 plus x. Or if you want to put these in the usual order, this is x squared minus x plus 1, x squared plus x plus 1. And this, miraculously, is the factorization of that. Right? Okay. After problem 10 comes problem 11, which is the division algorithm for polynomials. So if you have polynomials f and g with coefficients in some field x, we can write f as g times some quotient plus the remainder. So g has to be non-zero. In fact, not just non-zero, actually a polynomial. So the degree of g is at least 1. So I can write f as g times q plus r, where either r equals 0 or the degree of r is greater than or equal to 0 and strictly less than the degree of g. So q is the quotient polynomial and r is the remainder polynomial. And we want to use the division algorithm, that is long division, when the f of x is the polynomial 3x to the 5th minus 2x to the 4th plus 7x squared minus 11, and g of x is x cubed plus x plus 1. So how do we do that? Well, it's long division. Divide g into f. X cubed plus x plus 1 divided into 3x to the 5th minus 2x to the 4th. I'll leave a space for a cubic term, plus 7x squared, leave a space for a linear term, minus 11. So x cubed goes into this, 3x to the 5th, 3x squared times. 3x squared times this is 3x to the 5th plus 3x cubed plus 3x squared. So I subtract this minus this, I get minus 2x to the 4th minus 3x cubed plus 4x squared minus 11. X cubed goes into this, minus 2x times. Minus 2x times this is minus 2x to the 4th minus 2x squared minus 2x. When I subtract, I get minus 3x cubed. 4 minus minus 2 is 6x squared plus 2x minus 11. X cubed into minus 3x cubed goes minus 3 times. So I get minus 3x cubed minus 3x minus 3. I subtract, I get 7x squared plus 5x minus 8. And x cubed doesn't divide into a polynomial of degree 2, so I'm done. And this polynomial is my quotient, and this polynomial is my remainder. It has degree less than or equal to 2, and strictly less than 3. So my division algorithm says that my polynomial f, 3x to the 5th minus 2x fourth plus 7x squared minus 11 is equal to g, x cubed plus x plus 1, times the quotient, 3x squared minus 2x minus 3, plus the remainder, which is 6x squared plus 5x minus 8. So this is my quotient q, polynomial. This is my remainder r. That's my long division. Any questions about that? Problem 12, the last exercise where we calculate things, is symmetries of an equilateral triangle. We already saw that in the context of permutations of 1, 2, 3. So let's say this is my equilateral triangle. And R1 is a rotation by 2 pi over 3 radians. So 1, 2, 3 gets rotated 1, 2, 3. R2 is a rotation around the center by 4 pi over 3 radians. So 1, 2, 3 gets sent to 1, 2, 3. And E is the identity, 1, 2, 3, in that same order gets sent to 1, 2, 3. And the 3 by 3 multiplication table, we actually already did this calculation in the context of permutations. The identity doesn't change anything, so EE is E, ER1 is R1, ER2 is R2, R1E is R1, R2E is R2. R1 times R1 means rotate once and rotate again. That's rotation twice. R1 by R2 means rotate twice and then a third time. Well, when you rotate a third time, you're back where you started. And the same, R2, R1, rotate once and then 2 more times, you're back where you started. R2, R2, that maybe is the only one that's a little tricky. If you take your triangle and you rotate it twice, you get 1, 2, 3. Everything goes around twice. If you rotate it again, 1 goes here, 2 goes here, 3 goes here. So R2 times R2, this is just a single rotation, that's R1. So that's R1. So that's problem 12. So these are all the computational problems on the review sheet. Questions about these? All right. So the second half of the review sheet I'll go over, I think, on in our next class on Monday. That's a series of proofs. But if someone has a particular question now about any of the exercises I just did or the proofs, I am very happy to answer them. Any questions about any of this? If not, then I guess we can retire for the morning. Again, I remind you, we have a problem session on Zoom today at 1 o'clock, a problem session on Zoom Friday at 11 o'clock, and other sessions I can set up on demand if you simply send me an email and request some additional problem session time. Okay. Any questions before we quit for the morning? Okay, I'll be well. See you at on Zoom again, either in a problem session or a class.